Nucleophilic substitution is a really common reaction mechanism. We've covered it already with hydroxide and cyanide ions, and both of them are virtually the same mechanism, well, they are identical mechanisms, and they're really simple. Just 2 steps, everyone's happy. Nucleophiles attack the carbon, carbon-halogen bond breaks, the nucleophile and the halogen substitute places. That's nice and straightforward. We're now going to move on to another type of nucleophilic substitution that's a little bit trickier. And this time we're going to use ammonia as the nucleophile. So I've written out the equation that's going to happen. Bromoethane is going to react with ammonia. We're going to make ethylamine and ammonium bromide. So if you look carefully at that equation, there's a couple of things you should notice which are a bit different to what happens when you're doing it with, let's say, a hydroxide. First of all, the substitution isn't perfect, shall we say. A bromine doesn't swap entirely for an ammonia. What actually the bromine swaps for is an amine group, an NH2. So something has to happen to the other hydrogen. It's not just like there's a spectator ion and the OH and the Br swap places. This time the bromine and the ammonia swap places, but then a hydrogen has to get lost. So that's a little bit different to start off with. And then the second thing to notice is when we did it with a hydroxide or cyanide, it was a 1-to-1 ratio. One of the halogenoalkanes reacted with one of the hydroxide ions. This time, one of the halogenoalkanes reacts with 2 ammonias. So just by looking at that, it should tell you something odd has happened. Something is different. It's not the same mechanism perfectly. There's something else going on. Now, those of you that are really observant will also notice that what's formed, the other product, the ammonium bromide, some of the ammonia has gained a hydrogen to become ammonium. So that hopefully helps you, help you understand where that hydrogen that's disappeared from the amine has gone to. So let's draw the mechanism. First thing to do, draw out the bromoethane. Again, we're doing this with bromoethane, but it could be any halogenoalkane. The mechanism would be identical. Once we've drawn out the halogenoalkane, we're going to pop on our partial charges. So a delta plus on the carbon because the bromine is more electronegative, so the bromine will become delta minus. And that's the only polar bond. That's the only thing that's going to make the bromoethane more reactive than plain, straightforward, everyday ethane. And it's that bond that something's going to happen to. Now, the first step, we're going to draw the ammonia, and we're going to pop the lone pair on there. So ammonia, it can act like a nucleophile because it's got a lone pair which it can form a bond with. And what's going to happen is exactly the same first and second step as you would get with hydroxide or cyanide. Ammonia is acting as a nucleophile, so we're going to have a curly arrow going from the lone pair to the carbon. And let's even label this ammonia as a nucleophile. So it's donating its pair of electrons, forming a bond. That's why it's going to be a nucleophile, attracted to the positive charge. So now that's going to try and form a bond with the carbon. Therefore, the carbon will have 5 bonds or 10 electrons. That's far too many. It doesn't want that many. It wants to lose one of the species attached to it. And the carbon-bromine bond is going to be the easiest one to break. The bromine's more electronegative. It's kind of got the electrons closer to it anyway. So now let's take the electrons from the carbon-halogen bond and give them to the bromine. Curly arrow, clearly starting from the bond, definitely pointing to the bromine. Don't let there be any ambiguity for the examiner. Now this time, we're going to draw what's actually been produced. So nothing's happened to the left-hand side of the molecule. Probably not really left-hand side in real life, so you could look at that direction. And we're going to stick the NH3 group coming off the end here. Now, and don't forget that we've also formed the bromide ion. So we'll stick that down there. It's got a minus charge. Now, this is where things get a little bit tricky or a little bit different, and you have to think a bit more carefully. In organic chemistry, every time you draw nitrogen, it should normally have 3 bonds. So in ammonia, it's got 3 single bonds to hydrogens. When you draw an amine group, it's got a bond to a carbon and 2 bonds to hydrogens. But we've definitely got a nitrogen here with 4 bonds, and that's not quite right. So if we think what actually went on in this first step where it acts as a nucleophile, originally the ammonia had its lone pair of electrons. Both of those electrons belonged to the nitrogen. When it formed a bond with the carbon, suddenly it's now sharing those electrons. So we can almost think of it that one of the electrons still belongs to the nitrogen, the other one belongs to the carbon. So if you think about it like that, the nitrogen has lost an electron. Technically, it's still in its outer shell and still forming a bond, but the electron which was entirely belonging to that nitrogen now is having to share with the carbon. And because it's sort of lost that electron, the nitrogen now has a positive charge. Now, that isn't a partial positive charge. It's not because of a difference in electronegativity. This time, the nitrogen has a full positive charge, a formal positive charge, because it did have a lone pair of electrons. Now, one of the electrons, it's sort of donated to the bond. Technically donated both of them, but you can think one of them belonged to the nitrogen, one of them belonged to the carbon. So that second intermediate step that we've got there, the nitrogen, the NH3 group at the end, the nitrogen has to have a positive charge. Now, if we've got an excess of ammonia, which we have, let's draw our next or second ammonia just here. So let's remember that we formed that bromine, but we're going to get rid of it for now because it just gets in the way. Now, what could happen now is we've got a second ammonia because we've got 2 ammonias in the chemical equation. So we need to have that second ammonia coming in from somewhere. It's in our reacting mixture. If this ammonia acted as a nucleophile, it might be attracted to the nitrogen with a positive charge, but it doesn't. This step, it does not act like a nucleophile. It acts as a base. Now, when we talk about acids and bases, in their most fundamental sense, I suppose, plenty of debate about how best to define these, but an acid is a proton donor, a base is a proton acceptor. So the ammonia is going to act as a base. It wants to accept a proton. And what is a proton except for a hydrogen with its electrons not there? So when it acts as a base, it's going to take away one of the hydrogens from that NH3 group. And that's a good thing if you're the nitrogen atom. If you take away one of the hydrogens, which is acting as a proton, you can lose your positive charge, and it doesn't want to be charged. So the ammonia, when it acts as a base, is going to try and steal the hydrogen off the NH3. And we represent that with a curly arrow going from the lone pair on the ammonia, pointing to the hydrogen. So even though the ammonia is going to take the hydrogen away, the curly arrow has to point from the ammonia to the hydrogen, because that's what it's attacking. It's attacking that hydrogen to form a dative bond and form ammonia. Acting as base because it's taking away the proton. Now, you might be thinking, but hang on a minute, hydrogen does have an electron. but that electron that was around the hydrogen actually is in the nitrogen-hydrogen bond. And one of the electrons from the nitrogen is also in the nitrogen-hydrogen bond. So what's going to happen is both of the electrons in that bond are going to go onto the nitrogen. So the ammonia acts like a base, takes the hydrogen away from the NH3 plus group. We call that deprotonation. It deprotonates it. It takes away the proton. And the electrons in the nitrogen-hydrogen bond go to the nitrogen. And that will also get rid of that positive charge. So now what we've formed, again, nothing happens to the carbon on the left. Nothing really happens to the other carbon, to be honest. But it's lost now one of its hydrogens. So we've got an NH2 group, we've got the amine group, we've formed the ethyl amine. Let's put down the Br minus that we formed in the first step. And when ammonia acted like a base and took that hydrogen away, what did it form? NH4 plus the ammonium ion, sorry. And then the ammonium and the bromide, they come together to form ammonium bromide. Now, for this reaction to happen, obviously we need to consider the conditions like we do with all reaction mechanisms. We need excess ammonia. Otherwise, the second step won't happen and we'll end up with some kind of salt between the ethyl NH3 group and the bromine. We also need heat and reflux, or heated under reflux. That will encourage it all to react. But the most important one, this is done with an ethanolic solvent. So it's all dissolved in ethanol. And that's the key condition for this one that you need to know. And that is nucleophilic substitution with ammonia. It starts off the same as with hydroxide, but then there's a second step, which is a bit more tricky, where the ammonia acts as a base.